Welcome back to the deep dive. We've got a stack of papers today that reads less like a standard release and more like a forensic analysis of a very specific moment.
A bit of a mystery.
Exactly. You probably remember the Pony Alpha anomaly on OpenRitter, right?
Oh, yeah. Hard to forget that one. It was the classic mystery model drop. Anonymous endpoint, zero documentation, just raw inference.
And the community just went wild. People flagged it immediately because it wasn't just, hallucinating less.
No, it was handling really complex reasoning tasks. The fidelity was so high, everyone assumed it had to be, a leaked Claude Sonnet 5?
Or a secret OpenAI checkpoint. That was the other theory. The perplexity scores were just too good for it to be a standard open source fine-tune.
The consensus was definitely proprietary giant.
But the reveal was actually GLM-5, the new foundation model from Zhipu AI and Tsinghua University. And that is what we are digging into today.
We have the technical paper, and it's a masterclass in architectural optimization.
It really is.
Yeah.
And the authors are framing this whole thing not just as a performance bump, but as a genuine transition from what they call vibe coding.
Which is basically human-guided prompting.
Right. A transition from that to agentic engineering.
And that's a non-trivial distinction. Agentic engineering, in this context, it implies a system that can autonomously plan, implement, and then iterate, all without a human constantly in the loop.
To do that, the underlying architecture has to be different. You can't just keep scaling up dense models.
No way.
So let's get right into the specs. We're looking at a 744 billion parameter model. But, and this is key, it's a mixture of experts architecture.
Right, and the granularity here is really interesting. It's a 256 expert MOE.
That's a lot.
It's significantly higher than the 8 or 16 experts we often see in, Western models like Mixtral. During inference, it only activates about 40 billion parameters.
So it's in that sweet spot. High capacity, but a manageable inference cost.
Exactly. And it scored a 50 on the Artificial Analysis Intelligence Index v4.0. That puts it right at parity with Claude Opus 4.5 and GPT 5.2.
The very first open weights model to cross that threshold. Now, the paper leans heavily into the architectural efficiency needed for this, especially with context length. They've adopted DeepSeek's sparse attention, or DSA. We've talked about sparse attention before, but how is GLM-5's implementation different, especially for handling these 128K to 200K context windows?
Well, the challenge with long context, as we know, is the quadratic complexity of that attention matrix. It just explodes.
Right, it becomes computationally impossible.
So DSA gets around this by moving away from static sparsity patterns. Typically, you'd see something like a fixed sliding window or a strided pattern.
Okay.
DSA uses a dynamic selection mechanism. It performs a sort of coarse-grained query to identify the most relevant blocks of tokens first.
So it's basically doing dynamic query routing for attention at every single step.
Precisely. It filters out the noise before the heavy computation ever starts. They're reporting a reduction in attention computation by a factor of 1.5 to 2 for long sequences.
Wow.
But the engineering detail here, and this is critical for anyone training these, is the dense warm-up. You can't just train sparse attention from scratch. The gradients are way too unstable.
Right. The model would struggle to learn which tokens are even relevant if it can't see all of them at the start.
Exactly. So they use this dense warm-up and sparse training adaptation strategy. They start with full, dense attention to let the model establish those retrieval patterns, and only then do they transition to DSA.
That avoids the convergence problems, but keeps the speed-ups.
It's the best of both worlds.
Okay. Moving down the stack, let's talk attention heads. They're using multi-latent attention, or MLA. But the paper details this really fascinating conflict between MLA and the muon optimizer.
This was a highlight for me. So MLA is fantastic for KV cache compression because it projects keys and values into a shared latent space. But it usually lags behind grouped query attention, GQA8, in raw performance. So to bridge that gap, Zhipu tried using muon, which is a momentum-based orthogonalizer. The problem is, standard muon applies that orthogonalization to the up-projection matrices as one single monolithic block.
Which means all the heads are being normalized at the same scale.
Correct. But in a complex attention mechanism, different heads often need to update at different rates. They're tracking different features.
So they needed more granular control.
Exactly. Their solution is what they call the muon split. They split the matrices for the different heads and then apply the orthogonalization independently to each one.
So it decouples the update dynamics.
Yes. It lets the projection weights converge much more effectively. And it's pretty much the main reason MLA in GLM-5 actually matches the performance of GQA8.
They also made a specific tweak just for inference throughput, something they call MLA 256.
Yeah, this is purely an inference time optimization. In standard MLA, decoding can get bottlenecked by the projection overhead. So what they did was increase the head dimension from 192 to 256, but they reduced the total number of heads by a third.
So it's a trade-off.
A trade-off that keeps the parameter count the same, but cuts the FLOPs needed during decoding. It's just smart engineering baked into the architecture.
Another optimization that jumped out at me was the multi-token prediction, MTP. We saw this in DeepSeek v3, but GLM-5's implementation is a little different with the parameters.
The core concept is similar. It's like speculative decoding, but during training, you predict, say, same future tokens at the same time to densify the training signal.
And DeepSeek v3 used a separate MTP module for each of those future tokens.
It did. GLM-5, on the other hand, shares parameters across 3 MTP layers.
Wait, so the same weight matrix is predicting the token at T+1, T+2, and T+3.
Yes. It seems a bit counterintuitive, I know. You'd think the same transformation wouldn't apply, but it acts as a form of regularization. It keeps the memory footprint identical to a single head output, but it trains the model to accept longer speculative chains.
And the results?
They report an acceptance length of 2.76 tokens. For DeepSeek v3.2, it was 2.55. That difference might seem small, but when you're talking high-throughput serving, that is a significant latency reduction.
Let's shift gears to the training pipeline. The scale is just immense. 28.5 trillion tokens.
It's a staggering amount of data.
But the context extension phase, going from the base model to the 200K version, used a methodology I found pretty novel. They didn't just guess where to put the sliding windows.
No, this is what they call data-driven architecture. They used a search-based method on the ruler benchmark.
Okay, so when they were extending from 32K to 128K, they had to decide which layers would keep full attention and which would get sliding window attention.
Exactly, and instead of a fixed pattern like, say, window, full, they ran a beam search to find the pattern that maximized performance on ruler.
And the pattern it found was unusual.
Completely non-standard. The optimal pattern was something like sliding, full, sliding, full, sliding, and so on. It totally outperformed any fixed interleaving.
So that suggests the need for global context isn't uniform across the model's depth.
That's right. Some layers are just acting as local processors, while others are serving as these global aggregators.
Okay, so once the base model is trained, we get to post-training. The authors introduced this framework they call SLIME. It's very focused on asynchronous reinforcement learning. Why the big push for asynchronous?
Well, in an agentic context, a single rollout is it's incredibly expensive.
Because the model is actually doing things, right? It's writing code, executing it, parsing an error.
Exactly. That whole cycle can take seconds, maybe even minutes. Now, if you're doing synchronous RL, your learner GPUs are just sitting there, totally idle, waiting for that to finish.
Just burning power.
Yeah.
Huge bubble in the pipeline.
Right. So asynchronous RL just decouples the two. You have your inference engine generating stuff and the learner engine training on it, and they don't have to wait for each other.
Which maximizes your GPU utilization, but it introduces that off-policy lag, doesn't it?
It does. The data the learner gets is generated by a policy, let's call it pi theta old, that's slightly behind the current policy.
And you have to correct for that.
You do. And to handle that mathematically, they implemented 2 key things. The first is token in, token out, or TITO.
TITO, that's to deal with the retokenization problem, right?
It is. In a standard pipeline, you might pass the generated text back to the learner, which then retokenizes it. But tokenization, it isn't bijective. Boundary shift, special tokens can get dropped.
And for RL, you need a perfect one-to-one mapping between the action you took and the reward you got.
Exactly. TITO preserves that correspondence by passing the raw token IDs directly, bypassing text reconstruction altogether.
Okay, and the second part, to handle the mathematical divergence of that off-policy data.
That's where direct double-sided importance sampling comes in. This is mainly a memory optimization.
How so?
Standard importance sampling needs you to compute that probability ratio between the new policy and the old one. To do that, you typically have to store the old policy checkpoints.
Which takes up a ton of VRAM.
A massive amount. GLM-5 avoids this. It stores the rollout log probabilities directly and uses that as a proxy for the behavior policy. Then they just apply a clipping mechanism to control the variance of the gradient updates.
So they can train continuously on slightly stale data without the crazy memory overhead.
That's the idea.
Let's look at the RL algorithms themselves. They split it into reasoning, agentic, and general RL. For reasoning, they modified GRPO by removing the KL regularization term.
That feels aggressive.
It is an aggressive move. KL divergence is usually there to prevent the model from reward hacking or just drifting into nonsense.
It's a safety rail. Right. But their argument is that for reasoning tasks like math or coding, correctness is binary. You're either right or you're wrong. The KL term just acts as a brake on optimization. By removing it, they let the model shift its distribution much more rapidly toward the correct solution space.
There was also a really critical note in the paper about the DSA indexer, something about determinism during RL.
Oh, that's a crucial gotcha for any systems engineers listening. The DSA indexer uses a top K operation to select experts or tokens.
Okay.
On GPUs, standard top K kernels are often non-deterministic because of how parallel reduction is ordered. In RL, that noise is fatal.
Why?
If the model selects different tokens for the exact same input just because of hardware randomness, the policy gradient becomes incredibly noisy. It can lead to entropy collapse. They had to enforce a fully deterministic torch.topk operator to get the RL training to be stable at all.
That is a deep cut. Okay, so moving to the core value proposition, agentic engineering. They distinguish this from vibe coding with three thinking modes: interleaved, preserved, and turn level. Preserved thinking seems to be the real game changer for long tasks.
It is. It's all about tackling the state maintenance problem.
Right.
In a normal chat, every new turn reprocesses the history, but that internal thought process that led to the last decision, it's gone. The model has to basically rederive its own logic every single time.
It gets this kind of amnesia where an agent might forget why it decided to refactor a class 3 turns ago.
Exactly. So preserved thinking treats the chain of thought like a persistent object. It just carries over from turn to turn, decoupling the reasoning state from the conversational output.
And this was validated in the Vending Bench 2 results.
That's the business simulation benchmark.
Right. It requires maintaining a strategy over a simulated year, managing inventory, pricing, refunds, everything.
And how did GLM-5 do? It ranked number 1 among open models with a final balance of $4,432. The nearest competitor was around $2,300. That massive variance isn't just about better coding, it's about statefulness. The model maintained a coherent business strategy over hundreds of steps.
They also mentioned a specific strategy for search context, this keep recent K idea.
Yeah, this is a neat heuristic optimization. For web browsing tasks, they found that keeping the full history of every page visited, every DOM tree, it just introduces too much noise.
So they truncate it.
They do. By folding observations older than 5 rounds, they improve their browse-com performance from 55.3% to 62.0%. It suggests that in really dynamic environments like the web, local state is often much more predictive than global history.
We also have to talk about the hardware. This model wasn't trained on a stack of H100s. It was adapted for the Chinese chip ecosystem.
Huawei Ascend, more threads, Haigan. Yeah.
That requires a full stack adaptation, doesn't it?
Oh, absolutely. The software ecosystem there isn't as mature as CUDA, so ZPU had to write a bunch of custom kernels. They mentioned one called the latency indexer.
Fusion kernels are pretty standard for latency hiding. But what are they fusing here?
They fused the score calculation, the RailU activation, and the top pace selection all into a single kernel dispatch to minimize memory RW. They also use something called MLAPO, which fuses 13 different pre-processing operators into one super operator.
And what about quantization?
They used a W4A8 mixed precision scheme, weights at 4-bit, activations at 8-bit, specifically for the MOE experts.
Which can be tricky.
Very tricky. To make it work without degrading the model, they used Quarot for outlier suppression. This is critical because outliers and activation magnitudes can totally destroy the accuracy of 4-bit quantization. Quarot basically rotates the activation matrices to smooth out those spikes.
So let's synthesize all this. We have an open weights model using 256 experts, dynamic sparse attention, and asynchronous RL that is matching proprietary frontiers like GPT 5.2.
I think it validates a very specific thesis, that architectural specialization, things like DSA and MOE, combined with really rigorous agentic RL, is the path forward now.
It's no longer just about brute forcing the parameter count.
Not at all. It's about the model's ability to handle these long horizon state-dependent tasks.
So it effectively moves the benchmark from can it write this one function to can it maintain the state of this entire repository and implement a feature across multiple files.
Correct. The shift to agentic engineering means we're evaluating models on their ability to act as autonomous loops, not just as simple request-response generators. And GLM-5 proves that this capability is now fully accessible in the open ecosystem.
Which leaves us with a final question about deployment. If open models can now autonomously plan and execute complex engineering tasks, and do it on consumer-accessible hardware thanks to these quantization techniques,
then the barrier to entry for creating autonomous software agents has effectively vanished.
the tooling is here. The question is no longer, can we build it?
It's, how do we integrate it?
A paradigm shift indeed. Thanks for joining us on this technical deep dive into GLM-5.
My pleasure.
We'll see you in the next one.